the compositional elements style image. Can the Zoom hear me?
Yes, Zoom, could you confirm if you guys can hear us?
Right. And so in the other direction, we're projecting the compositional elements of the style. So we have this open patch of sky right here in the content image, and we want to project like the basic composition of the source image onto this open patch, which doesn't have like structural form. Okay, so the main challenge is going to be how do we represent the content of the content image and the style of the style image in a way that will allow us to minimize the loss of those two elements respectively. So this isn't an object recognition task, not a classification task, because we're not trying to just output whatever the content, whatever the style is. We want to somehow get a latent space of the content and a latent space of the style and project the two onto each other. And so what we can do is we can do transfer learning on a pre-existing object computer vision model. And so this is BGG16, which is the successor to AlexNet on the ImageNet dataset. And so this is a like heavily pre-trained deep convolutional neural network that already is going to like elucidate some of the latent space of our content structure and hopefully hopefully can elucidate some of the style structure, which we'll get into what that really means. But it's already trained up, and so we can just like use it right off the bat. The only nuance here is that the last fully connected layers have been trained on a classification task. And so as we convolute the image down the network, these last layers are turning this convoluted image into a classifier for the ImageNet data set. So they would say what the subject of the photo is. And for that reason, we're just gonna chop off the fully connected layers and take the trained convolutional layers. Yeah. What's pooling? That's a good question.
So basically, each convolution layer's goal is to, you have an image, but image is big and it has a lot of details. Each convolution layer looks at the small details. Let's look at a small example. So, for example, as Josh talked about, we have a clock tower here. So how does the algorithm know there's a clock tower here? It looks at the small parts of the image, and the convolution layer interprets the clock tower and outputs the whole layer is essential to convey the next information to the next convolution layer. Because if you just give the output of the convolution layer to the next one, then you cannot, your algorithm will suffer from overfitting and other problems. So full layer is essential for that.
Did I answer the question? Okay, so we're going to look at what convolution actually looks like for the content image. So this is like progression as we feed forward through the convolutional layers. And you can see that it's doing exactly what we want, which is that it's no longer focusing on the composition of the content image, but it's focusing instead on like the higher order structure. And so this is obviously a image representation of what the latent space has learned. But we imagine that sort of picking up, okay, here's some sort of high order structure. This might be something like a house, and this might be a window and another house. And so we're elucidating the content and, alleviating the compositional elements. And for this reason, our content representation can immediately be the activations of the convolutional layers at the deep layers of the network. So, for example, if we have an activation, some arbitrary activation in a deep layer, it might be firing exactly for the presence of a house in some region of the input image or a window in some region of the input image. And it is no longer firing for whatever like basic composition makes up that object. Okay, so we look at what the convolution does for the style image. So similarly, it's going to forward through the convolutional layers. And there's a bit of nuance of how do we represent style. And I think that's like the main point of this paper is how do we extract style from a style image? And I want you to think for a little bit about what makes up style in a style image, because personally, I don't find the representation immediately compelling. Immediately does it grab style? But the paper suggests that style is the co-occurrence of features at multiple layers. And so it's most intuitive, I think, the lowest layers. The lowest layers of the composition capture things like horizontal edges, vertical edges, dots, circle structures, different basic structures like this. It also captures things like soft edges, hard edges, colors. And this style representation ends up being a measure of the co-occurrence of these features. So for a given region, you're measuring, do horizontal lines co-occur with soft edges? And are swirls yellow? Like in the Starry Night, if you can see this, like here we have a yellow swirl. And so we might imagine that yellow swirls are a stylistic element of Starry Night, or that blue swirls are a stylistic element. And we also have this measure of co-occurrence at like multiple layers of abstraction in the convolutional network. So even at a high end, you can capture stylistic elements. Like if you have, I forget the artist who does like French street art and he plays with like political themes. Are like police officers present with children? These are also kinds of things that you can elucidate at really deep convolutional layers. And the actual implementation of this, which we'll see in the engineering part, is this thing called a Graham matrix. And so each of these vectors of the Graham matrix is the feature map of a particular convolutional layer for each feature. And so like at the lowest level, the green vector might represent the presence of horizontal edges at some spatial region. And the blue could be vertical edges, yellow could be green, and dots and so on. You take the and you vectorize this and create this like sort of augmented matrix. And by taking the transpose of this matrix, you can take the dot product of each respective vector. And this Graham matrix becomes a measure of the co-occurrence of each of these features. So then we present our prediction. And at the beginning, our prediction is just going to be like noise. And we're going to iterate over the white noise and try and minimize the loss function between content and style. So we define our style loss or content loss, I think we begin with. Right, so we're going to take a linear combination of content style loss. Well, I'm probably going to revisit this once we talk about what these things are. So the content loss immediately is going to mean mean squared error of a very deep convolutional layer. And for example, if you have this deep convolutional layer here, this might be capturing things exactly like, is there a clock tower in this region of the input image? Is there a house in this region of the input image, or a river? And for that exact like mean squared error, we're saying, does the predicted image have those basic structures in those basic regions, regardless of what the composition of those structures is? So as for the style loss, we're going to take the difference between the Graham matrix of the prediction and the Graham matrix of the style image. And we're going to do this over multiple layers. So we're going to take the first convolutional layer, compute the co-occurrence of features in that layer, and compare it to the co-occurrence of features in a prediction image. Then we're going to do it for the next layer and the next layer and so on. And we're going to do like weights over these layers. I can't speak to the significance of these weights, I believe there's different arguments that style is like more present at different convolutional layers. I think you'd imagine that some artists' style might be more present at deeper convolutional layers if it's more style in terms of content. And then like some styles like Van Gogh, I'd imagine we heavily weight the lower convolutional layers because he has a very like strokey, lots of soft edges, and these are the things that would be captured at a shallow convolutional layer. And then, as we said before, we take a linear combination of these two functions, and we can actually train the coefficients to sort of strike a balance between content and style, because we want the respective losses to be similar so that we're not biasing towards either content or style. Yeah. And then, as I'm sure many of you are familiar with, we're going to essentially compute the gradient of the loss function and step along the gradient over many iterations until we're able to minimize the loss function for a prediction image. And so, for example, we have the coefficient for style, and this shows what happens as the style coefficient increases. And here's some more results. So this is a previous, on the left is a previous neural style transfer technique. And so we can see we're maybe capturing the content a little bit better with the new method. And then this is going to be an overview of the full pipeline, I believe. So is there any questions? Yeah.
So can you use this to improve image quality rather than looking at an art style to another one? You can just improve a current image quality by like having a proper correct image where it's supposed to be an image like you could put a camera.
So I think it depends. My intuition, and I'm not completely positive, but I think it depends what you mean by quality. I would imagine that if you have like an animation or image with low quality and you do style transfer with a photograph, that it would be able to like improve the quality. But I certainly don't think this would be the best model for this task. There's going to be many models and techniques that are better for that kind of task. But I would imagine that might be a use case for some input. Yeah.
Any other questions?
Okay, cool. So we have a QR code for the Jupyter notebook, and Berke is going to take over for the engineering.
So you can scan the QR code, or we have a URL at the top as well. So if you could just check out the Google Colab. Sorry, guys. Did everyone get the link? If you're working on your computer, entering the URL might be easier. So just so you know. It will be, yeah. All right, then. I will show you how we start. So I copy paste the URL. This takes me to the Google Colab. And if you look at the Google Colab, we have some code, but it's not full. For example, like this part we will have to fill. So you should not be able to edit this, right? You can't edit this. You can just view this. So what you want to do is go here, file, and then set a copy in Drive. Let me actually show you. It opens a copy of the document. This is it. And then you can edit here. So let me go back to my original document. Okay. Okay, is everyone ready to go? Okay, so let's start. So introduction. So as we already did the introduction, I'm Berke and Joshua made the presentation. And this tutorial is actually from PyTorch. So we have to give credits to them. And let's talk about the underlying principle. So we talked about content and style losses. We will use two distances for them, a distance for each of them. And then DC measures how different the content is between two images, while DS measures how different the style is between the two images. Then we take a third image, the input, and transform it to minimize both its content distance with the content image and its style distance, so that at the end you will have something that resembles the style of the image, and then it has the content of the image that we want. So let's talk about some packages that we have. We will be using PyTorch, as we do in most of the HackTheMist workshops. So Torch and NumPy, these are packages used in neural networks. NumPy is a great package, like it's a de facto package in Python for math computations. Torch.optimi will use for gradient descent. I will talk about that when the time comes. And then PIR is great for image visualization. Torch vision.transforms. We will transform our images so that our model is not overfit. It can be used in real world. And then Torch vision.models to pre-train our model, we will use VGG16, and then to deep copy the models. And then we also have matplotlib inline. This ensures that when you use matplotlib, it doesn't open a new window, but it prints it under the Google Colab. So the first thing that you want to do is run this. So I will run this. Okay. Is everyone copying what I'm doing? And then if you check the folder, I lost mouse. If you check the folder, you can see I don't have anything. I just have this. Ignore this. So I want to get the images. We already uploaded the images to GitHub. So what you want to do is clone the GitHub repo. This takes like 10 seconds. After 10 seconds, you must have the images here. So I come here and I can see this is HackTheMist workshop art. So it's at the top. You want to go to that folder. We also have other workshops here because we have been doing workshops since the beginning of the year. And then I have the images here. We will visualize these images now. If you don't see the folder here, you might want to close this and open it again. So did everyone manage to copy the repo? Yeah, okay. So let's proceed. And then, so Kudo is a device that we can use to make our algorithm run faster. So normally our computer uses CPU, but with PyTorch, we can use CUDA. So it works on their end, not our end. So let's try to get CUDA. Sometimes it doesn't work. So if it works, we will use CUDA, so it will be faster, as I said. So now let's talk about the first task of this workshop. We want to load images. So we will import the style and content images. The original PLI images have values between 0 and 55. This is the values for any pixel, like any image in a pixel. And then we will transform into torch tensors. Torch tensors are used for PyTorch computations. It's like arrays of values, but torch values, torches are, you can manipulate torches faster. You can use, like, your algorithm runs faster if it's a torch instead of an array. And then, so enough of the talking, let's just start doing. So the first line of code we have here, we set the size of the image, and then use a small size if you don't use GPU. And then we load the images, we just resize them. We don't do a lot of transforms in this workshop because if our goal was to classify some stuff, then we would want our model to not overfit, and then we would want our model to transform images. For example, if all the images are like bright, and in real world the image could be not bright, then you would want to transform images so that some of the images are not bright. But our goal is not to classify stuff. Our goal is to produce something that looks good. So we don't transform images here. And then we will load image here. And at the end, we will visualize these images. So let's start coding. Okay. I will delete this line. You should do it, or you can just write it underneath. So the first thing that I want to do is get the image for style image. So I will say style image is equal to image.open. I'm using the PIL library for this. And I will get the style path. The next thing I want to do is do the same thing for content images. So I will just copy paste and then content path, content image. After this, I want to have both of these images to have the same size. Otherwise, my algorithm sometimes doesn't work good. So I will just resize the style image. So I will just say style image is equal to style image dot resize content image dot size. So this will ensure my style image has the same dimensions as the content image. Next, I want to load my image using PLL library because this just opened the image, not loaded. So let me just load it as well. And I want to unsqueeze because this might have more dimensions that we want. So I will just unsqueeze the first one. Do the same thing for content images. So now I've imported the images and I loaded the images. And at the end, I just want to return those. So I could just return the images, but I want to return them so that our model can use them directly. That's why I will not return style image directly. I will just say style image to device. I will convert it to a torch array. And then I will do the same thing for content image. So I'm returning a tuple, if you know Python. Content image to device torch dot float. Okay, and then at the end, I want to call this method, so I will just copy the method name. And then I'm giving two paths to this method. The first path is the style path, the second path is the content path. So I go back to my folder. It's hard to find the mouse here. Okay. So I open the first folder, and then first folder inside this folder, and the first folder inside this folder again, and I have the images. So for this workshop, let's use Van Gogh for style, and then the only content we have is Toronto. So the first thing that we put in style path, so I will get the path here, copy path, come back here. I will say copy paste. And I forgot the double quote marks. Okay, now we copy paste. This is the first path. I said comma. To see it better, I will just enter. And I will enter the second path, which is Toronto image. Again, I will put two quotation marks, put it inside. And let me try to run this. Let's see if I made any errors. I mostly do, so, but this time I didn't have any. So, any questions regarding how we load images? I can take any questions, but yep.
Why does unsqueeze do?
So sometimes the image might have alpha values as well. We don't want that. So unsqueeze just sets the dimensions correctly. We want to have like 3 dimensions for each image.
Okay.
So if everything's okay, I will proceed. And then here we have another method. I will keep that on top as well. So this method, we will unload images here. Let's see. Now we want to display the images. So let me just write a small code to display these images. We will use my matplotlib for this. So I will say, I will first set the figure for matplotlib, and then I will just use IAmShow to display the image. Let me give it a title. let's say style image. Do the same for content. Let me run this. So now I got the style image and the content image. If you want to try another style, you could use the Salvador Dali or Pablo Picasso templates we have. But for this workshop, let's stick with what I'm doing so that you can follow me. Okay. Then let's proceed. Loss functions. As we talked about in the slides, we have a loss function for content and loss function for style. What we want to do is minimize these loss functions, but we can't minimize two functions. What we want to do is get a linear combination of those and then minimize the linear combination. So at some point, we will have to sacrifice some loss in style and sacrifice some loss in the content so that we can find a middle way. So let's start with content loss. Content loss is simple as we talked earlier. Maybe a little bit more complicated, but we will talk about that as well. We use gram metrics for style. So let's start with content then. Here we are using NM module. NM module is a great model in PyTorch, which does all the work that we want. So since it's a subclass of NM module, I can just call the super class. So I will just say super content loss self. And I will just initialize this. This way, the superclass does all the work that I need to do. And then I will modify self.targets. So we use detach the target content from the tree used to dynamically compute the gradient. This is a stated value and not a variable, and otherwise the forward method of the criterion will throw an error. So we use detach for that reason. And I come to forward. Here, I want to compute the loss and then send the input. So I compute the loss using the input I have. Again, let me define what loss means. So your loss is basically how far you are from what you want. So you want to minimize the loss. And I can just say self.loss. In machine learning, we usually use mean squared error, and there are other methods as well. But for this workshop, we will again use mean squared error. So mean squared error loss, and for the input, I will just say input self.target. And what I want to return the input. I just want to get the input, give the input, and while doing this, I want to calculate the loss. Any questions here?
So,
Yes.
we're making loss function, we can linear combination of as many variables as we want.
This does not use linear combination. This is just the loss of the content loss. We will compute content loss, we will compute style loss, and then we will look at the linear combination at the end. Does that answer your question? Okay. So after you do this, you have to run this block of code. Does the Zoom screen see this? Okay. This is content loss. It was simple. Let's talk about style loss, which is a little bit more complicated. So let's dive further into it. So I will just shoot the text here to define what we are doing. The style loss module is implemented similar to the content loss module. It will act as a transparent layer in a network that computes the style loss of that layer. In order to calculate the style loss, we need to compute the gram matrix, as we talk about in the slide. A gram matrix is a result of multiplying the given matrix by its transpose matrix. In this application, the given matrix is a reshaped version of the feature maps. And then we want to reshape this form back, and then like people use gram matrix for this purpose. You can just read it. I'm not going to read all the math notations. And the gram matrix can be normalized by dividing each element by the total number of elements in the matrix. This normalization is to counteract the fact that the FXL matrices with a large n dimensions yield larger values in the gram matrix. So a lot of theory, but let's just start coding. So we have given the gram matrix, so you can just use it. We're not gonna code gram matrix. And then we are gonna code style loss. So it will again be, we will first call the super function, call the super class. And then while doing the forward function, we will use gram matrix because we just don't want to calculate the loss from the input. We want to take the input, put it into gram matrix, get the result, calculate the loss there. So let me start by calling the super function. And then I want to do the same thing for targets, but this time the target also goes through the gram matrix. That's how I initialize the style loss. Next thing I want to do a forward function. So let me do that as well. Again, I'm using mean squared error, but this time I'm getting the mean squared error of the gram matrix. At the end, I will return the input as well. So two things to notice. The first thing is we put target into gram matrix and get the targets there. So when you put subdot target here, this isn't the original target we have. This is a target after we put it through the gram matrix. So we put input into gram matrix, we put target into gram matrix, and then we calculate the loss there. If this is also okay, let's run this block of code as well. Okay, now let's proceed. We said we are using VGG19. This is a pre-trained model, and we said we don't use the last 3 layers. We just use the pre-trained weights, and then we will put our images into this, and then we will get the output of this. So PyTorch provides VGG19. So let me just run this block of code to get that. As you can see, it's huge. And then we want to normalize because VGG networks are trained on images with each channel normalized by mean equal to this, and then standard deviation equal to this. So we want to transform our images to fit into expectations. Because in machine learning and also in statistics, if what you train on is not applicable for what you see in real world, for example, you have a data of people aged between 0 and 18, and then you input a people that's age 60. Your model is not going to predict accurately, so you have to normalize both the mean and standard deviation. So we provided this code as well. Let's just run this. And then we will get the style model and losses. We will compute losses here. So a sequential model that the VGG19 has contains an ordered list of child models. For instance, VGG19 features contains a sequence, convolution 2D, ReLU function, maxpool 2D, convolution 2D, ReLU, repeated again, aligned in the right order of depth, we need to add our content loss and style loss layers immediately after the convolution layer they are detecting. To do this, we must create a new sequential model that has content loss and style loss modules correctly inserted. So for content layers, we are just using convolution 4 layer. And for style layers, we are using all these 5 layers. So we put more layers into style. As we said, we use the gram matrix in style. So in most of the workshop, we do most of the work in the style part. And in the content part, we just do a small part of work. So let's start by normalizing our input. And then I want to get an array of content losses and style losses. We will fill this ourselves. It starts as an empty array. And here we have the main for loop. So this for loop iterates all these convolution layers. And during each iteration, we want to compute the loss value. So this part of the for loop looks which layer we are at, and then this part of the for loop computes and stores content losses. So right now we have to fill this part where we look at the loss values. The other parts are detailed. So let's start with here. The first thing that I want to do is get the targets. So I'm gonna say target equals model content image dot detach. This will put the content image into my model, and I will get the target from there. The output of the model is the target. Next, I want to compute content loss. And this is equal to, we have defined a content loss class. So I will just input my target here to get the content loss. So this is one content loss. And remember, we have a content losses array at the top. So what I can do is first add this model to my model. I can say content loss dot format I. This is detail. You don't have to worry about this too much. And then I can put my content loss here. And more importantly, in my content losses array, I want to attend my content loss. Is this okay? Like what we are basically doing is we get the image, we put the image into our model, the VGG19 model, we get the output, we compute the content loss of this output with this line of code. Remember, we defined content loss above in the class. And then we add this as a module into our model, and also we add this to our content losses array so that we can keep track of the loss values. So I will do the same thing for style layers. I will say, let me modify this style image, and then let me give this a different name. Let me say target feature, and then style loss, which takes in target feature, and then I add my model style loss at the end. I add my array style losses where my input is style loss. So this is just using the previous things that we have defined. We are using our model that we defined earlier. We are using not content loss, style loss that we have defined earlier. And we are adding the results into an array. Then we trim off the layers after the last content and style losses using this for loop. And at the end, I expand my model once more, and then I return my model style losses and content losses. So what did we achieve here? Let's go back all the back to the top. So as you can see, this method gets your model, your CNN, your images, and then computes the style and content loss of both of these. So how are we gonna use these loss values? Like how are we gonna progress from these loss values? That's the next part of the workshop. So after writing this, I need to run this. Then I come here, run this. And gradient descent. This is where we start the gradient descent. So we need to get the optimizer. So the optimizer that we are gonna use for this workshop is actually Optim. Let me write this. I will pass in my input image as an array, so I need to do this. Otherwise, it gives an error. Input image. And for example, you're a curious person that wants to learn more about this optimizer. How can you learn more? So you come here. It doesn't let me do it. Okay. Yeah. I'm on Mac. I press command, and then I could click the blue link that appeared underneath. And then I can see the source code here. So if you're curious about that, you can check the source code. But it's usually complicated. So I will just run this block of code as well. Now I got the optimizer. So now I want to do gradient descent. So I need to get the initial loss values. I can do this by creating a couple of variables. First, I need a model. I need an array to keep track of style losses. I need the same array for content losses. And then I think that's all the things that we want. So I will just say get style, model, and losses. So my inputs are CNN, normalization mean, normalization STD, my style image, content image. So this is nothing new because we are using the same methods that we defined above. So when we first start, we start with empty values. Like we start with initial values. These values are usually random. So I run my model once with these values, get the model style loss and content loss. And in a while loop, I will repeat this for the number of steps that we predefine. So we take a number of steps as an input for our function as well. Right here, the default value is 500. 500 will take like five minutes. So you might want to reduce that, but it will improve the performance. So let me come back here. I say model that requires grad equals to false. This is because I don't want to train VGG19. I want to train all my own images. So my image requires grad, which means I will keep improving my image, but my model doesn't require grad because I don't want to improve the model. As we said, the model is pre-trained. So I will come back here and let's look what we want to do. We want to get the optimizer here. So let's get the optimizer. We will just say optimizer is equal to get input optimizer, and then we will pass in the input image here. And then the next thing that we want to do is instructed here. We want to compute losses, evaluate scores, and then call the back propagation algorithm. So let's start doing that. The first thing that I want to do is set my optimizer. So I will say 0 grad. Again, I want to improve my images, not my model, not my optimizer. I want to improve my images. And then I will put my input image here. Get the style score to be equal to 0. Same thing for content loss, content score. Next, I will create a for loop. So for S1 in style losses, because remember, style losses is an array. I want to increase my style score. There is a more efficient way of writing this using array.sum function, but we will keep this because it's more readable. Then I will do the same thing for my content losses. Let me just write it as well. For C1 in content losses, I will increase my content score. C1.loss. So again, our style score keeps track of style losses. Our content score keeps track of content losses. And we want to minimize both of these scores. In the next line, I will multiply my style score by the style weight. These style weight and content weights are defined by the model again. So I'll do the same thing for content losses. So any questions here?
How to store the optimized value.
Okay, let's talk about optimizer. So we imported optimizer. We didn't write the optimizer ourselves. And when we do this step, optimizer step here, it automatically computes the gradient descent. So let me give you an example. Let's say this is a two-dimensional image. Okay, so what I have here, let's say this is alpha as style plus beta L content, and this is the. Actually, I want to have this as the alpha as style plus beta as C, and here this is alpha and C, alpha and beta values. Okay. Assume this is one dimensional for the sake of visualization. But usually my loss function is like this. And I want to find the global minimum of this function. So as you can see, the minimum is here. But let's say at the start of our iteration, our alpha beta values are quite low. So we start like somewhere along here, okay? We are here. How does gradient descent work? We are here, take the derivative. And if you look at the derivative, it tells me to go down. So for some constant, we go down, and this is where I'm at the next iteration. I take the gradient, it tells me to go down. I go down, go down, I go down, and I find the global minimum. When I come to the global minimum, the gradient is 0, so it tells me to not move. So that's how the gradient descent works. And here, optimizer does that for us. So we don't have to write the gradient descent from scratch. But that's basically the idea of the many machine learning models. So let's wrap it up. The last thing that I want to do is get the style score and content score. Here, I will keep the linear combination as just 1, 1. You can play around with that. And this should be it. Yep, let me run this now. Okay. Now let's run the algorithm actually. Let's see if you have any errors. I'm expecting errors. Yep, there's always. So I said in-out optimizer, let me go there. I need to run this code again. Come back here, run this again. Actually stop it because I need to reduce the number of steps. Let's say 100 to make it faster. Okay, so I did 50 steps. My star loss is quite high. My content loss is quite high. So I'm doing another 50 steps. I'm creating my losses in 50 steps. And in only 100 steps, this is what I have. Thank you for coming to this workshop. Unfortunately, we run out of time. So if you have any questions, I can take one question. Then we have to move on to the next workshop. Any questions? That's great. I will upload the final version of this into GitHub. I will share it on Discord so that you guys can see it. And thank you for coming.